Hello, welcome, Shirtloads of Science with me, Dr. Carl, and my friend of the show who hasn't been here for too long, Professor
Geraint.
Geraint. That's a Welsh spelling.
It's a Welsh name even.
Welsh name. And that's a Welsh person on your T-shirt.
Owen Glyndŵr.
And what was he famous for?
Welsh freedom fighter.
Right. And relating to the fact that he was trying to fight the people who were invading his country, the English.
Yes.
Who invaded, out of the 200 countries on Earth, they militarily visited all except 12. But they even got to Tibet, but they didn't get to the Vatican. Okay, getting back to you, it's been too long since we talked, so look, I'm so happy to be talking with you again. And you're my go-to guy, and I was going to talk about some things, but then this popped up in the New Scientist. Apparently, when some galaxies collide together, things can happen, blah, 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 little bullet. Therefore, there's no dark matter in them. Therefore, dark matter might be a particle. Can you turn this into English for me?
Okay, so this story is about a group of galaxies. Okay, so the galaxies living together.
Yep.
And often in those scenarios, galaxies collide. And
Galaxies can collide.
Yeah, bits and pieces get thrown out, right, in the collision. So what they've got here in this story is they've got a string of dwarf galaxies.
A string of... So our galaxy is an old and big one.
Yes.
11 billion years old, as you point out to me, and 300 billion stars, something?
300 billion, plus or minus 100 billion.
But this one is a dwarf?
Galaxy, yes.
And how many stars would it have?
Couple of billion.
Okay.
So it's quite small compared to the big galaxies.
Yep.
And the question is where did these dwarf galaxies come from? Because they find them strung out like a string of pearls.
Oh,
yeah.
So geometrically, when you look at it with a telescope, you go boop, 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 boop. They're strung out like a string of pearls. How does that happen?
So the idea is that maybe when in the collision, you've got a big stream of gas that gets ripped
Collision
off.
between two bigger galaxies?
Yes.
And they don't actually have the stars go bunk, bunk, bunk against each other, except very rarely, if ever. But normally they go through each other.
Yes.
But the gas?
The gas can get flung out. So gas gets flung out, and you imagine a long streamer of gas.
Yep.
And then in that gas, when some parts of that gas starts to cool, it collapses down. And it collapses down and it forms a chunk of stars, which are these dwarf galaxies that are formed in collisions. So they're tidal dwarf galaxies.
Okay, so let me get this straight. You have to get to roughly 70-ish the mass of Jupiter before a pile of gas can self-ignite and then form. That number's still roughly right. My memory's okay?
Yes.
Okay,
Yeah.
so you've got this gas which is not stars, but when you get enough of the blobs of gas, one here, one there, then you can get a star here. Okay, right.
Right.
Does that happen a billion times to make a billion stars?
Oh, yeah. These gas clouds will fracture into all these little pieces. So the gas clouds are big. They contain an awful lot of mass in there, and they can basically all collapse down and give you millions to billions of stars.
Right. Okay. So, we got that much. So the galaxies collide, and as a result, stars are formed because blobs of gas reach that 70 times Jupiter mass, and then ignition, hydrogen plus hydrogen, and off it goes.
Yes.
Okay, right.
Right. So the question is about these dwarf galaxies, which are tidal dwarf galaxies.
Oh, the string of pearls that you mentioned at the beginning.
Yeah. Are they the same as other dwarf galaxies that we see? Because we see lots of these little galaxies in the universe. And most of the galaxies that we can see the stars, but it's thought that there must be lots of extra mass, lots of dark matter there, whose gravity holds these dwarf galaxies together.
Okay, just for the audience, this is going back to Vera Rubin, and she was seeing that the galaxies were spinning at a rate during the Doppler thing. They were spinning so fast they would fling apart unless... Can you take it over?
Yes, unless there's extra gravity there. So it's like having a ball on a string, and you push the ball around. There's a tension in the string, and the faster you make it go around, the bigger the tension is. So for stars orbiting in a galaxy, that tension is the force of gravity.
Yeah.
And if you want a star like the Sun to orbit around the Milky Way at 220 kilometers per second,
that number is still roughly right. Yep.
Which is what our velocity is, then you need more gravity than can be provided by all of the other stars you can see.
So in our galaxy, the Milky Way, they seem to be all going at 220 kilometres a second from close in to far out, unlike in our solar system, where they're doing, 50 kilometres a second or something for Mercury, 30 for Earth, and 4 for Pluto way out in the stick. So how come they're all travelling at the same-ish orbital speed?
So in the solar system, there's one source of the gravitational pull on the planets, really, right? It's all dominated by the sun. 99% of all the mass in the solar system is in the sun.
90%.
Yeah, so some huge number, right?
Right.
So that provides the gravity, and that gravity then drops off with distance.
Yep.
But in the galaxy, it's not like there's a
galaxy, the
in
Milky Way.
our Milky Way. It's not like there's a single mass in the center which is responsible for all the gravity.
Even though we've got a 4 million times black hole, solar mass black hole in the middle, that's not enough.
That's irrelevant.
That's irrelevant.
Compared to the billions of stars, right? I mean,
Okay,
right? So
of
4
course.
million solar masses is less than 4 billion solar masses of all the stars. And we keep going up. We've got hundreds of billions of solar masses. So if you look at the mass distribution in the Milky Way, it's not concentrated at the center, but it's basically spread out. It is peaked in the center, but then spreads out as we go out. So inside every orbit, there's a bit more mass. And this is why it doesn't drop off like in the solar system. There's basically a constant gravitational pull, an additional gravitational
spread
pull.
out across the entire Milky Way galaxy.
Absolutely, and beyond.
And beyond.
And well beyond.
And this is the putative supposed dark matter, which we still haven't solved yet.
We don't know what dark matter is. The prevailing theory is that it is a particle, i.e. it's a subatomic kind of thing. There would be a lot of it.
I've heard the word axion.
Axion is one kind of dark matter. The problem that we have is that we have many theories with many dark matter candidates as part of those theories.
Yep.
So you get axions and WIMPs and axinos and all these kind of things. But they all basically do the same thing. They produce extra gravity because they've got mass. So we can't really tell one theory apart from another one, just due to essentially the gravitational pull that we're seeing. There's some subtleties there, which is why there's these experiments to try and capture dark matter in the laboratory. So not that far from here in Stawell, underground in Victoria, in a gold mine, they're building the Stawell laboratory, Sabre, where they're building this very sensitive detector, which is trying to basically capture dark matter inside that detector.
If it's one sort of putative particle.
One or possibly many, right? There's some thoughts that dark matter might interact with normal matter, and that's what they're trying to find in these experiments.
That's the important thing. Dark matter cannot be observed by any of our telescopes,
Not
going
directly.
from gamma, X-ray, ultraviolet, visible, ray, microwave, infrared. No, we can't pick it up with those. We can pick it up by gravity. It does have gravity. Dark matter does have a gravity.
See, a way a physicist would say is that dark matter ignores electromagnetism, which is light is an electromagnetic
Really?
wave. Yeah. So it ignores electromagnetism, but it feels gravity, it interacts via gravity. So it's like it's the only force that it really interacts with. But there might be a possibility that there'll be other weak interactions with like atoms and things. And that's what they're trying to detect.
Okay, so before I diverted you onto this little background explanation of gravity, you were saying something about galaxies having or not having dark matter. So can we go back to that before I took you down this rabbit hole?
Yes, so this group of galaxies that we're talking about here, this is a system which has been in the news over the last 5, 6, 7 years. For
the astrophysics, physics, cosmology, astronomy news.
It would have been in New Scientist, no problem, right?
Okay, right.
In there, originally there was a galaxy called DF2, right? You have to remember this is astronomers really, boringly naming things.
And DF...
I can't remember what the DF stands for.
Dark force.
Something. But it's number 2, and there's 3, 4, and 5 of them as well.
Okay.
So people had found this small galaxy, and they were trying to measure how much mass it had. And so they were doing that by looking at how fast these small groups of stars called globular clusters, which have about 1 million stars each in them, they buzz around the big galaxy, and the rate at which they buzz sort of tells you how much mass should be in that galaxy.
So they're a fairly dense, compact bunch of stars, and so whereas our nearest star is 4 light years away, that might be 1 or 2 light years away.
Oh, closer.
Or closer.
Oh, closer, yes.
So they're a glob,
yeah,
and they're a cluster, and they're fairly small. We've got. Do we have any orbiting our galaxy, the Milky Way?
Yeah. Some number around 100.
They're out in the sticks, though, out in the edge.
Oh no,
no.
There's some towards the center as well, but they don't orbit in the disk with the stars. So our Milky Way is a disk of stars,
like 2 soup bowls face to face.
Yeah,
Yep.
and then globular clusters are generally going like this, over the top and under the bottom, kind of thing. So they're not
really?
not constrained to be in the disk, but they move around in what we call the halo.
So they're associated with this. Okay, so getting back to the globular clusters and the measuring and the dark matter, because I've distracted you again, sorry.
Yeah. So this system DF2,
Yep.
they measured the amount of mass as indicated by the globular clusters and then added up the mass that you see in the starlight, and they say, oh, you basically get the same answer.
What?
And so they suggested that DF2 was a dark matter deficient galaxy.
So it's deficient.
Right.
We think ish.
Yes, but you have to remember that
How do you measure it?
well, these things are difficult to measure, and then you've got to think about all of the other complications, right? Because you get complications involved about, does this thing rotate? Because rotation changes the picture.
Yes.
Has it interacted with another galaxy? Well, this story has told us that there have been galactic interactions in this little group of galaxies anyway.
So the two galaxies collide. Yep, okay, got that.
So you've got to make some assumptions when you try and estimate the mass. And the normal assumption you make is that the phrase that we use is the galaxy is relaxed.
Oh, really? Is this special astrophysics, astronomy, cosmology talk?
It means something. It means basically settle down, right?
Yeah.
So even if there were things like violent collisions in the past, that was all in the past, and everything's now settled down.
Settled down.
And when things settle down, then you get nice relationships between how fast the stars moving, etc. But if it's not relaxed, if it's not in equilibrium, right? If it's dynamically, all over the place, then your mass estimate by making that assumption is going to be off.
Oh my God, how do you tell the difference between a relaxed and what's the opposite of relaxed? Non-relaxed?
Yes, well, listen, yeah.
Okay, right. How do you tell the difference?
That's why these guys are doing these measurements, right?
Right.
They are now, I think they're looking at the systems to try and say, right, have there been collisions? And if there was a collision, how long ago was it? And how close was it to this object, etc. So they're trying to build a dynamical picture of the life of this group of galaxies to tell them whether or not the DF2 result is weird or, is it really a dark matter deficient galaxy?
Well, what struck me from this article in the New Scientist, page 19, 5th of July, was I was saying, okay, so they probably are devoid of dark matter, so that's reasonable. And then they say, I don't know who wrote this, the dark matter doesn't interact with matter or even itself. Is that true? Does dark matter not even interact with itself?
Again, words have to be careful. Dark matter is thought to interact with itself gravitationally. Right? Dark matter pulls on dark matter. There are some ideas that dark matter, being a particle, can interact and now and again, take two dark matter particles, you crash them together, they produce something like gamma rays. But those again are those theoretical ideas rather than something we robustly know.
Okay, so they're saying that while the gas, when the two original bigger galaxies collided, when the gas was torn from the galaxies, dark matter was unaffected.
That's right.
So what the dark matter just sort of kept on going, ignoring what the gas was doing. And what was the gas doing what it was doing? Because it was affected by gravity?
Yes, so gas is complicated, right? So when we talk about dark matter, all you really need to worry about is essentially its density, right? Because it doesn't do anything other than gravity. All you care about is how much mass is there.
Right.
Now, gas on the other hand, can do lots of stuff.
So would gas be an individual hydrogen atom or two atoms together to make a molecule? Or what?
It'll be a mix of all of that stuff. It'll be mainly hydrogen.
Yep.
Right, and it might be a mix of ionized hydrogen and a bit of molecular hydrogen, etc. So galaxies have, and this is why gas is difficult. Even if you want to talk about the simplest element, right, you've got to talk about ionized hydrogen which has lost its electron, neutral hydrogen, which is holding on to its electron, and molecular hydrogen, which is two hydrogens stuck together.
Yep.
They behave differently.
Each of those behave differently.
Right. So you end up with multi-phase medias, that's a phrase that
and that's only hydrogen, there's all the other possible elements, but hydrogen's the big one.
But just think about like the gas in this room, right? What you could do, right? If you heated the gas in this room, you could turn it into a plasma. Right.
So you could strip the electrons off.
Yeah.
Okay. All of them or just the other?
It depends. You can strip some off, you can strip all off. It depends on the temperatures and the collisions.
Really? So if you get the temperature high enough, you can strip all the electrons off the oxygens?
Yeah. You can tear them all off.
Keep going. I don't distract you.
But of course, you can do other things. You don't have to heat it to the extent where it ionizes. You could just heat it up. And that hot gas is different to cold gas.
Really?
Right?
Even that?
Yeah, if I chill
Wow.
the gas down, it settles down on the floor.
That's a different...
I can compress gas, I can rarefy gas. And of course, gas in space, right, where we've got lots of mass and we have to worry about what gravity's doing, big gas clouds can start to collapse and form stars.
Under their own gravity?
Yeah.
Yeah.
And then those stars release energy, which goes out and hits the gas. So the entire sort of ecosystem of what goes on in gas in space is very complicated. And you should talk to some of the people that try and model this stuff. It is lots of various processes going on. So that gas which comes off, right? The dark matter leaves, the gas that comes off, as I said, cools, collapses, forms stars. That's a very hand-wavy picture of really what's a lot of complicated levels of physics going on in this debris from the collision.
And that gas is no longer attached to the dark matter that it was attached to gravitationally beforehand?
No, this stuff will have separated, but it will start to respond. I mean, those galaxies will still be in the vicinity, so the gas will still feel the dark matter and might start following it again.
Okay, so then it goes on to say, this could refute ideas for dark matter that suggest our evidence for its gravitational influence result from a mismanagement of how stars and galaxies form. And this is saying that dark matter is a particle. Have I misread that?
I haven't read the words. Let's have a look.
Mismanagement.
That says mismeasurement, Carl.
Mismeasurement. Okay, I can't even read properly no more. So it's a mismeasurement.
There are questions around, how did these forms, and are they similar or different to the other dwarf galaxies that we see, which are dominated by dark matter? Because these guys, they don't have that dark matter to hold them together.
Yep.
So once they formed stars, they too themselves might start to disperse. So whilst a dwarf galaxy might live for billions and billions and billions of years, these tidal dwarf galaxies, they might just be around for a billion years and they've completely evaporated.
Hang on. You're saying that if you've got a dwarf galaxy of, say, 1 million or 1 billion stars, it does not have enough gravity from the mass of those stars to hold itself together unless there's dark matter?
Generally, yeah, that's right.
How do you measure this?
Well, we can measure the speeds at which stars move around inside dwarf galaxies. So that we have dwarf galaxies
Do you have a fancy name for that?
Spectroscopy.
Right, okay.
Yeah, and the Doppler shift. So we don't want to give away our secrets, though, because it's all really simple at the end of the day, right? But we have nearby dwarf galaxies where we can see individual stars and we can measure their velocities, and that reveals how much mass is there.
Do you give that a fancy name like velocity, dispersion, variation?
We talk about how the velocity dispersion, how fast stars are moving towards or away from us, is related to the gravitational pull that's there. Because if something has to exist for a long time, you can't have its stars escaping. So even though they might be moving, let's say, at 5 kilometers per second that way, eventually they'll have to slow down and come back to stay part of the object. If they're moving up,
because if they don't slow down,
then they exit stage left.
and then you end up with a dwarf galaxy evaporating. Is that
yes?
Is that, it doesn't have a central. Okay, the central black hole wouldn't have enough mass.
No,
generally like a billion, unless it was 1 billion.
No, these things, if they have black holes, and then they tend to be relatively small
in mass. Okay, so the dwarf galaxies can evaporate.
Well, these tidal dwarf galaxies, they have no additional mass holding them together. So, yes, they thought that they would evaporate.
So I'm still confused about dark matter, though. So it's not like an even mesh that spreads everywhere in the universe. It's sort of clumped.
Absolutely.
Dark matter is clumped.
Absolutely. That's right. Yeah. So the dark matter in the overall Milky Way is clumped. The density gets higher towards the center. So even though dark matter doesn't interact very much, that gravitational interaction still pulls things together such that you get more in the middle, less on the outside. Right? So every single galaxy you'd go to, so next door to us we have Andromeda. It too is surrounded by its own dark matter halo, which is concentrated in the middle and is gets less dense on the outside. And these halos, they are much larger than the galaxy that we see.
Oh, really?
So Andromeda is 2 million light years away.
Yep.
So the light we get left Andromeda before there were humans on Earth. right? In roughly 4 billion years, Andromeda will be here, i.e. the two sets of stars will collide.
Well, there have been articles saying that maybe they won't collide, maybe they will, depending. They might miss.
I have thoughts in that paper, but we'll talk about that
another time.
Yeah.
Okay.
But the dark matter halos are so big is that the collision has already started.
A what?
The outer layers of the Milky Way and Andromeda are already coming into contact.
Okay.
It's very low density stuff, right? Because it's the outskirts of these dark matter halos which drop away, but they're already coming into contact.
If the visible mass, as accounted for by the 300 billion stars, and a black hole is 1, what is the mass of the dark matter associated with our galaxy, the Milky Way?
Well, somewhere between 10 and 100 times.
Really?
Yes.
So significantly greater?
Significantly
not
greater.
like 0.5
No,
or
no,
1.5, but like 10 to 100, somewhere in that.
And the uncertainty comes from the fact is that it's very difficult to map that dark matter, right? We sort of know what's going on in the vicinity of the sun because we got all the stars going around. But going out into the halo, how do you know how much dark matter is over in that direction or over in that direction? And we're only now really getting to grips with the question of what's the shape of the dark matter halo. So we basically hand wavy, I said that 10 to 100, right? It'll be a number something like 50 or 60 or something like that times. But yeah, there is a lot more dark matter than visible matter in the galaxy. In fact, the visible matter is barely the icing on the cake, if you think about it. Right? The universe would happily operate without any stars, right? Without any atoms. Right? So we're made of atoms. That's all sprinkling. It's only a few % of the universe.
We're kind of, you and I are just rounding errors in the universe.
Yeah, well, yeah, that sounds like a happy thing to say.
Okay, now just to finish off as we come to the end. So we've got the galaxy, the Milky Way, like a couple of soup bowls face to face. And the globular clusters, they're on the outside and the inside. And then, but I think you said once we're in a local group of galaxies, about 20 or so that sort of buzz around their common centre of gravity like a bunch of bees?
It's slightly more complicated than that.
Of course it
right?
is.
So we live in the local group.
Yep.
Right? So most galaxies in the universe are in groups. So galaxies don't like to be alone. And some of them live in clusters which might have thousands of galaxies there. Thousands of galaxies like the size of the Milky Way. We live in a group, and the group is dominated by two large galaxies, us and Andromeda.
Ah, we're the two big guys.
We're the two big guys.
Yeah.
But then there's a bunch of slightly smaller galaxies, so M33, Triangulum.
I've heard that name.
Yeah.
So that's one of us, is it?
Yeah, and also the Large Magellanic Cloud, which we can see in Australia.
On a dark night.
On a dark night.
Have you ever seen it on a dark night?
Yes.
What was it? Tell us the circumstances.
Well, I'm an astronomer, so I often go to observatories, and it's often dark.
Because for me, the first time I was out at Coonabarabran, where they've got a big telescope there, and they were giving me a guided tour, and they said, luckily it's a moonless and cloudless night, so you got a good view. And I said, what do you mean a cloudless night? I can see a cloud over there. And that was the Magellanic Cloud. And that was the first time I saw it as a cloud, as the sailors would out at sea a long time ago. I didn't realise that it actually looked like a cloud.
Yeah,
I thought
absolutely.
I thought it was a cloud of water droplets, not a cloud of stars.
And of course, it's got a little friend. It has the Small Magellanic Cloud nearby, and looks like they're a binary pair of small galaxies. The Large Magellanic Cloud is bigger than the Small Magellanic Cloud, but they look like a pair of galaxies that have fallen in together.
And in our local group, are there any dwarf galaxies? That's what I was trying to head
Oh,
for.
yes. There's probably around 100
What?
dwarf galaxies.
I thought there were only 20 things in our local group. So
No.
So we're being mean to the dwarf galaxy. We don't really count them, do we?
So the number of dwarf galaxies has increased rapidly as we have been able to image more of the sky. These things are hard to spot. And so you need dedicated surveys. Like there was the Sloan Digital Sky Survey in the 2000s.
Yeah.
Right? 1990s, 2000s.
Alfred P. Sloan or something.
Yeah. And now we're moving into the realm of LSST and Euclid and all these new...
Yeah, what's LSST? Large...
It was the Large Synoptic Survey Telescope, but now it's the Something Survey over Space and Time.
Okay,
I can't remember the details.
enough.
But that's at the Vera Rubin Observatory.
part of Vera Rubin?
Yes. Yeah.
Vera Rubin is the big telescope with the world's biggest camera, and each bunch... It's huge, and there's like a kilogram of processing per megapixel.
It's going to be crazy because what they're going to try and do is continuously image the sky, right?
So every couple of days?
Because
the whole sky?
Because they're after things that change, transient events, because we know that the things that go pop in the universe, we don't know what they are. But also, every time you go over the sky, right, and you add the images together, you get to see deeper, right? And so as they build up more and more data, we're going to find fainter and fainter dwarf galaxies because they're hard to spot, and there's probably lots of them which are very faint that are well below our current detection.
Right. So in our local group, as we come to the end, there are, when we now think 100 dwarf galaxies, would they have like 1 million or 1 billion stars each-ish?
It will vary. A few billion down to maybe hundreds of millions.
Wow. Look, thank you for being my go-to person. So I can just hit you with this and you go, yeah, blah, 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 and then you explain it to me. And that proves that you are truly knowledgeable in this field and I know nothing. And thank you very much for taking us through this and the dark matter update. And how do people, you're a professor here at the University of Sydney, how do people follow you in your fine work and become your student and hopefully get good enough to get you and them a Nobel Prize further down the line?
Well, I'm on Bluesky.
You're on Bluesky?
I'm at Cosmic_Horizons. I left the other place.
The other place?
The other place.
Okay. So Cosmic_Horizons. And you've written 4 books now?
Four books.
And the titles are?
A Fortunate Universe.
Yes.
Where Did the Universe Come From?
Yep.
Cosmic Revolutionary's Handbook. And A New Copernican Turn. And I just had a 5th book accepted called The Shortest History of Reality, which will be out mid-next year.
I won't ask how short it will be.
It's currently 60,000 words, but I think I've got to trim it to 50.
Right, okay. Look, thank you so much, Professor Geraint. Geraint?
Yeah.
I still can't quite do it. I can do the Lewis bit.
Yeah.
Thank you very much for doing it for me and proving that, once again, you're the go-to person.
Pleasure, Carl.
Shirtloads of Science is washed, spun and aired by the University of Sydney.